Now that we've set up the source particles and our collision object, let's go ahead and start setting up our actual simulation. So let's start by creating a DOPNet, and then dive inside here, and let's create a flip solver, and connect the flip to the output, and we'll need this to operate on a flip object. So drop in the flip object as well, connect it to the first input of the solver. And if you take a look at the flip object parameters, there are a few ways to initialize this. Under initial data and input type, you have a few different options, but we're going to select particle field. And for the SOP path, we'll open up our object picker and go up to our source particles null and accept that. And then if you rewind the sim to frame 1, then you can see all of our particles initialized in this simulation. Now let's go to guides and the second tab, particles. And the current visualization is set to sprites, which can be quite a bit heavier in the viewport. So I'm going to change this to particles. And you can also see here this gives you more controls for visualization. I'm going to leave this all alone, and this will show us the velocity with a color ramp. So that'll help us to get a good read in the viewport of what's actually happening in the sim. And then, going back to the top of our flip object parameters, we have these very important controls here. We have the particle separation, which should ideally match what we've set on the flip source as our input. So let's go back outside our DOPNet, and then go to our flip source where we've created our source particles. And I'm going to copy this particle separation parameter here, copy that, and then go down back into our DOPNet, and paste a relative reference to the particle separation here. So we can control this in SOPs on that flip source parameter. And in the introduction to flip video, I mentioned that the flip solver will use a velocity volume field to do some of its calculations to compute some new velocities for the particles, and this is creating that velocity volume on every frame, or I should say every substep. And that velocity volume doesn't necessarily need to be quite as high res as the particles, so we have this grid scale option here. And the tooltip gives you a hint that the default should be good for most applications, so you don't really have to worry about this, but this means that this is going to use a velocity grid resolution that's half the resolution of our particle separation. So the voxel size will be twice what we've set in the particle separation here. So I'm going to leave this set as it is, and then let's move on to bringing in our collision object. So we can add a static object, and for the SOP path, let's point this to the collision geometry null that we've already set up. That's this one here. And then merge this in with our flip solver. So I'll drop in the merge, connect the static object to that, and you can see that this shows up right away. But because the default merge option is for left inputs to affect the right, we need to swap these inputs so that the collider affects the particles. And then back on the static object, let's also point this to the VDB that we've created for this collision geometry. So under collisions, let's go to the volume tab here, set the mode to volume sample, so this directly uses a volume from SOPs without trying to generate its own. And then for the proxy volume, we can point that to the collide volume that we've already set up. So select that and accept. And now let's take a look at the flip solver parameters. So we can leave the substeps tab alone. I didn't find myself needing to change any of the defaults here for this simulation. Then on the particle motion tab, under behavior, we can turn off collide with volume limits because we don't want to simulate this like it's a tank that's containing all of the particles. Colliding with our bounding box for the sim isn't really going to help us at all, so let's turn that off. And let's turn on add ID attribute. It's always a good idea to add this because that gives us more options if we need to perhaps tweak the simulation with some post-processing after the fact. For example, if there's one little area where some of these particles are splashing out in a weird way, you could potentially select those after caching out your simulation and select those particles based on the ID attribute and delete them. If you don't add this ID attribute, then you won't have a consistent ID that you can use for that cleanup. That's just one little example of how that could be helpful. There could be a variety of things you want to use the ID for. Under reseeding, I'm going to leave all of this at its default. So what this will do is this will add particles when you have an area that gets too sparse based on the particle separation of the sim. So our flip object has our given particle separation here, so it's going to try to maintain this point density. That's where this reseeding comes in, because in our simulation, as things start splashing around and flowing, if particles get too thinned out in some areas, then this will help to fill that density back in. I'm just going to leave all that behavior at its default. The next tab, separation, will help to enforce that distance between particles. I didn't really find this to be necessary for the simulation, so we don't need to worry about that. Under the droplets tab, this can change how some of the particles that break free will behave and affect the simulation. And some of these options give you a lot of good information in the tooltips, so you can certainly check those out if you forget what some of these things do. So these droplet particles that break free won't be as influenced by the fluid forces, and they also won't contribute their velocity back to the fluid simulation. And the example they give here is that droplets falling back into the main body of fluid can have an unrealistically large effect. So turning on this extra droplet detection can help to address that, but I really didn't feel like that was necessary here. Under vorticity, it's important that we turn this on. This vorticity attribute can be quite important once we start adding whitewater to the simulation, because we can source more whitewater particles from those areas of higher vorticity. And this also could be potentially used in the shading as well. So just turn that on and we can leave these options at default. And then on the rest tab, this is going to add rest data that evolves with the simulation, and this can be helpful when you want to apply some extra noise in the shading process. I personally didn't bother with it for the final version of my shot. I didn't really think it was necessary. I'm just going to leave this turned off for now. And moving on to the volume motion tab, we have a couple different options for velocity transfer. This determines how the velocity is transferred from the particles to the volume grid that's used for solving and back to the particles. The default option flip, the splashy option, is what we're going to stick with here. The other option, apic or swirly, is generally used for simulations like perhaps lava, where it's very slow moving and you really want a very pristine surface for this. I believe this also could be useful for some very small scale simulations, but for something like our splashy river simulation here, let's stick with this default flip splashy option. The force scale determines how much of that new velocity change is applied to all of our particles. I'll just leave this at 1. The velocity smoothing option can be quite helpful as well. I'm going to leave this at its default for now, but of course you can tweak this up or down depending on if you want those velocities to be smoothed out or more energetic and splashy. For my final sim, I wound up turning this down quite a bit, but we can leave it alone for now. We can leave smooth surface and update surface and velocity on their defaults, don't need to worry about those. And now on the volume limits tab, we need to set up a bound for our simulation. So right now, it looks like our simulation particles exist everywhere, despite this bounding box only enclosing a portion of that sim. This is just the default bounding box setting on that flip solver. But if we step forward 1 frame, then you can see that it's thrown away all the particles outside of this bound here. So you could manually resize this box if you want. If you mouse over the viewport with the flip solver selected and hit enter, this gives you some controls to adjust the bounds here. So we can drag out this side of the box like that. Or as an alternative to manually sizing this up, you could define the bounds in SOPs. So if we jump out of our DOPNet and take a look at our area of interest, we can build a bounding box based on this. So I'll just drop in a bound SOP and connect the area of interest to that. And if you display that bound, then this is just going to enclose the entirety of our input. So this gives us a pretty good bounding box to use for the simulation. If you were expecting that you would have some splashes going higher than the bounding box here, then you might need to add some more padding to this. You can use these padding options here, or put an additional transform on the bound after this. But I think that what we have here is just fine. I'm not expecting these splashes to be going up super high, so just all the defaults on this bound are fine. And then I'm going to add a null after this, so that we can refer to this in our flip solver. I'll just call this bound. You could have the flip solver point to this bound node directly, that's called bound1, but I find it's always good practice to reference nulls instead of other nodes directly, just in case we wanted to do anything else to this bounds after creating it. Then we could apply those extra transforms or edits or whatever in between our bound SOP and the null. So after setting up that bound, let's go back inside our DOPNet. And for the box size, I'm going to use the bbox function and point that to ... So that jumps up 2 levels in the hierarchy that references our DOPNet with the first ... and then the river with the second ... And then we can just add /bound to refer to that bound null that we just set up. And then we'll add d_xsize to grab that size component. And let's copy this, tab over to the y size, paste that in, and change this to y size, and tab to the z size, paste that in, change this to z size. So now you can see that our simulation bounds inside the DOPNet are being sized to match that bound SOP. But we also need to match up the center as well. So under box center, I'll use the centroid function. Once again, point that to ... /bound, and then d_x to grab the x component of that center position. Then let's copy that, paste it into y, change it to d_y, then paste it into z, and change that to d_z. So now the bounds of the sim will perfectly match that bound that we set up in SOPs. Now moving on from our volume limits tab here, let's go to collisions. And we can leave all of these settings here alone, but I'm going to turn on stick on collision. So ultimately what this is going to do is slow down the particles when they collide with this other geometry here. If you didn't have stick on collision turned on, then all of these particles would be trying to flow just as fast as they're running along these collisions with the rocks and the side of the riverbed. But you would expect that the river would be a little bit slowed down at the edges there. Obviously, it's still going to flow fairly freely along those sides, so you don't want to push this stick-on collision too hard in the case of a flowing river. But using some of this stick-on collision will give us that nice slowdown effect on contact. And I found the defaults here to work pretty well, but you can certainly feel free to play around with that if you'd like. Viscosity we don't need to worry about. And we don't need to mess around with the density based on attributes. Don't need to worry about error incompressibility or any divergence by attribute. You don't need to turn on any additional surface tension. And I'm going to leave all of these solver settings on their defaults. And scrolling back up to the top of our flip solver, this narrow band tab here, we don't really need to worry about. What this will do is this will essentially simulate a narrow band of your flip volume here, and it'll make the center of it hollow, so it doesn't really have to simulate all of the particles in there. It will still compute that as filled space in the middle of your flip volume, but in a case like this river here, especially where it's fairly shallow, we don't really have a lot of space in here that we can optimize by using some narrowband computation. This narrowband option is much better suited for a deeper volume of water where you can just simulate a narrow band of flip on top of it, and it'll still behave as if the overall volume has much more depth. And then going over to the distribution tab, we don't have to worry about this. This is mainly just for doing distributed sims where your processing is split across multiple machines, and this is not something we're messing with here. So now that we've built the core of our flip simulation setup, let's go ahead and do a flipbook and see what this looks like. Now this simulation is looking quite cool, and it is aesthetically interesting, but this doesn't look much like I want it to for the end result. Everything is working from a technical standpoint. The simulation and colliders work properly, we're getting some initial velocity, but all the water is kind of flying everywhere. And that's because we forgot to add some gravity. So let's go back into our DOP.NET here, create a gravity force DOP, drop this after our merge, and then let's run a new simulation with the gravity applied. Now after adding gravity to the simulation, this river is starting to look pretty cool. Everything seems to be working nicely in the sim from a technical standpoint, and the river is dying off very quickly because we're just starting with a fixed amount of water volume here that's just flowing out, and it's not getting replenished with any inflow, and we don't have good control over how the water's flowing out either. So we're going to need to do some extra work to control that flow and maintain that velocity throughout the river, but everything is looking quite cool at this point, and this is a really good starting simulation before we go on to make some of those improvements.